So in this video I want to show you an application of Pascal's famous theorem to show that 6 points lie on the same conic. Okay. Now, as you know, if I draw any 5 points on the plane, save a few exceptions when there's some collinearity or some other degeneracy, I can always draw a conic through these 5 points, right? So here's P1, P2, P3, P4, P5. So I can draw a conic, or let me say it this way, there's a unique conic associated with 5 points in the plane. It's fully specified. Now, a situation in which Pascal's theorem comes into our rescue is if I actually insert into this diagram a 6 point. Let's put it over here, and I'm going to call this point P6. So here's P6, and I want to know, does this point lie on the same conic as the other 5? Or I could say it this way, are these 6 points conconic, as it is sometimes said, conconic? So for example, right now P6 does not lie on the same conic as the other 5 do. So if I actually moved P6 over to the conic, it would. And if I went inside, P6 no longer lies on the same conic. So let's actually now use Pascal's theorem to see how this thing works out. What Pascal's theorem says is if 6 points lie on a conic, the intersection of opposing sides of a hexagon that contains, or whose vertices are those 6 points, the intersections of opposing sides of that hexagon, the 3 intersections are collinear. So let's draw a hexagon, the simplest one. There's actually 60 different possibilities here. I'm going to draw a hexagon whose vertices are the 6 points on the screen. Now obviously P6 is not on the same conic, so we're going to see here that Pascal's theorem does not hold. But what does Pascal's theorem say? This is a hexagon, so it has 6 sides. Let me move P6 a bit to the top here so you can see here that this is a different side. So the sides are P1, P2, P2, P3, and so forth and so on. And I'm going to elect a first side, for example, P1 to P2. Which one is its opposing side? Since this has 6 sides, I need to skip 2 and find P4, P5. So what am I going to do? I'm going to draw a line through P1, P2. I'm going to draw a line through P4, P5. And I'm going to mark off the intersection of those 2 lines. And I'm going to call this intersection here. Let's give it a good name. Let's call it, so this is the intersection of 1, 2 with 4, 5. So I'm going to call it 1, 2 with 4, 5. Like that. So this is my first intersection. Okay. Now let's keep keep going on Pascal's construction. Now I'm going to take side P2, P3, like so. And I'm going to see where it intersects the opposing side. So that's, I have to skip 2, that's P5, P6. There it is. And you can see now that that intersection is happening way off over here. Okay, so to avoid this, what I'm going to do is I'm going to move this point just a tiny bit to bring this intersection closer over here. So now we can see everybody in the same diagram. And I'm going to mark it off. And I'm going to call it, you've guessed it, that is 2, 3 intersected with 5, 6. There it is. So that's my second intersection of opposing sides of my hexagon. Now there's one more pair of opposing sides, and that's precisely, so I've done 1, 2, 2, 3. Now there's 3, 4, correct? And who is the opposing side with that? That's skip 2, P1, P6. So let's draw those 2 lines. So here's P3, P4, and here's P1, P6. Again, that intersection is happening way out over here. So let's actually move, perhaps I'm going to move, let's see, who could I move? I could move P4 around a little bit, this way, so we can see that intersection over here. Now let's go ahead and mark that off. And I'm going to label that as the intersection of points 4, 5, sorry, 3, 4 with 1, 6. There it is. Okay, now what does Pascal's theorem say? If indeed these 6 points are conic, they lie on the same conic, these 3 points will be collinear. Now you can see that they're grossly non-collinear here. Now let's move P6 around a little bit and let's look at what happens to this construction. And what I'm going to do here is I'm going to first of all draw a line between 1, 2, 4, 5 to 2, 3, 5, 6, and I'm going to color this line, since this is our sort of our main highway here, main Pascal highway, in red. Okay, now for P6 to be conic with the other 5, and it's clearly not, okay, this point here has to somehow migrate and be collinear and lie on the red line. So you can see here that if I move P6 around, the moment P6 is on the conic, like so, I start approaching collinearity. In fact, if P6 enters the conic, I'm no longer collinear, and I have to wait until I place P6 somewhere else, for example over here, so collinearity is reestablished. Okay, so how do I know this? I'm tracking this line here that is emanating from P6 along P1, P6, and I'm seeing if its intersection with the opposing side is collinear with the red line. So you can see here that, let's go back to that side we were working on before. If P6 is on the conic, that intersection 3, 4, 1, 6 is going to be collinear with the other two which were worked out before. And let's go ahead and position them all on the same screen so we can see this even better. So let's take a look at this again. P6 on the conic, collinearity of the center point over here. P6 inside the conic, I break collinearity, and if P6 is outside the conic, I also break collinearity. So with GeoGebra, I can obviously attach P6 to this conic over here. Okay, so now P6 is attached to the conic, and as I sweep the conic, you're going to notice that collinearity is maintained. Look at how cool this is. Of course, I can change the other points at will, since they're all on the same conic. In fact, I've defined the black conic over here. Let's actually draw this conic here as color green. Okay, I've defined this one using the first 5 points on this list here. So 1, 2, 3, 4, 5. And P6 is the rogue point, and I'm trying to make sure that it actually stays conconic with the other 5. Okay, now I want you to notice another thing here. Notice that now the hexagon is self-intersecting. Okay, now you may ask yourself, when you picked the original hexagon to make this construction, okay, you decided to go 1, 2, 3, 4, 5, 6. Isn't this an arbitrary labeling or a biased labeling, right? Do I need to follow vertices in some order, counterclockwise order or clockwise order? And the answer is no. In fact, if you're given 6 points, you have 60 ways to enumerate them, and you have 60 distinct hexagons. Now, as soon as you actually come up with a labeling and an ordering, you're going to call this one the first, this other one the second, so forth and so on. All Pascal's theorem needs is that you respect that ordering when identifying pairs of opposing sides. Okay, so for example, if my ordering is like so, okay, I still am following this as P1, P2, P3, P4, P5, P6. So it's pretty well established which pairs of vertices are opposing to which pairs of vertices as soon as you establish an ordering. Notice that the ordering here is not monotonically counterclockwise or clockwise. Okay, so I guess that's what I have for Pascal's theorem. I'm going to do a series of videos that is going to build on this. We're trying to get to a synthetic construction of objects associated with this conic just using ruler and compass. And we're going to need this construction here to move forward. Anyway, I'll see you on the next video. Thank you.